Well, good afternoon. Welcome to the CLSP seminar, as usual. Our speaker this week is Gertjan van Noord from University of Groningen in the Netherlands. And a lot of you probably know his work in one area or another. For example, those of you who have been working on finite state things have all used his FSA Utilities Toolkit, which is excellent, usable, and extensible, and know about some of his other work in the finite state arena. He's done work on computational optimality theory, on grammar formalisms such as unification formalisms, and actually, as we'll see today, writing and building grammars for Dutch, for example, in those formalisms with statistics added, with efficient parsing such as head-clutter parsing and so forth. Dr. van Noord did his undergraduate degree and also his PhD in linguistics at University of Utrecht, and spent a year at Saarbrücken before going to Groningen. So, welcome.
Thank you. Okay, as you see, I've listed a number of colleagues on this sheet as well. So this is because what I'm going to talk about today is about, at least according to my standards, a very large project funded by the Dutch Science Foundation. It's a pioneer project. It's called Algorithms for Linguistic Processing. It's nice in general, so we can do whatever we want, I guess. But we've promised to focus especially on problems of ambiguity and efficiency. What I will be talking about today is essentially consists of three parts. First, I will give you a little bit idea of the background, so I will describe the system and some of its components. And you could sort of summarize the system that on the one hand it's grammar based, and at least we sort of attempt to implement sophisticated linguistics, so at least we call it sophisticated ourselves. And on the other hand, we are also very aware, and we find it very important to confront that approach with a corpus-based evaluation methodology. So we also really want to get problems solved. So it's a kind of a hybrid approach. And then I will go into a little bit more detail about two aspects, two recent techniques that we've, components that we've added. So I will be discussing a disambiguation component, which is a maximum entropy log linear disambiguation component. And so that's an aspect of disambiguation. And then I'll continue and I'll discuss a semi-supervised part-of-speech filter component, which we use to greatly increase the speed of the system. Now this, the background of the Alpino system contains of about 6 parts, and for each part I'm going to say very little, but so hopefully you'll sort of get an idea what kind of things are going on there. First I would like to sort of tell you how this work got started. The origin of this system is in a previous project, a Dutch project that was distributed over a number of universities, in which we were supposed to build a spoken dialogue system for, as always, timetable information of public transportation. And the interesting aspect of that project was that there were two competing natural language processing groups involved. So it was our group, and we were supposed to do what was then called conventional NLP, meaning without statistics and grammar-based. And on the other hand, there was a purely statistical approach being pursued by the group in Amsterdam, headed by Remco Scha, and Rens Bot was there as well, you might know. So they were pursuing a data-oriented parsing approach. And although we started out as a kind of a grammar-based group, it turned out that we were much more worried about actually solving the problems in this project. And in a formal evaluation, it turned out that actually we did quite a bit better than the statistical group. And I don't think that you can learn anything about whether statistics is better than symbolic approaches, for instance. But it's rather that you perhaps should combine them and perhaps should worry about getting the job done. So,
what is the evaluation?
Sorry.
What are the figures 84.1?
Yes. Okay, so there's 3 criteria. We can perhaps ignore the CPU column because it wasn't very distinctive anyway. So WA stands for word accuracy. This was in a speech project. We were parsing word graphs, and the idea was that you could sort of take the part in the word graph that belonged to the best analysis according to the system, and you could compare that with the actual utterance, right? What people had actually said. So
this is speech recognition?
This is so the speech recognizer produced the word graph. Then the NLP component had to sort of select a part from the word graph and assign it a semantic representation.
Word graph is what we call lattice?
Yes.
It's a lattice, sure.
So this is the standard speech recognition accuracy.
Right.
Yeah. It's
Right.
just that you didn't do the acoustic processing. That's what.
That's right. That's
What
right.
do you mean they didn't do that?
It means the acoustic processing was the same for both systems.
Right. Right. It's
So they rescore it.
Yes.
yes.
Do you take the acoustic score of a part?
Yes, we also took those into account, although they turned out not to be very, very helpful. But of course, there was already a lot of filtering going on before we got to that stage. Okay. And
So you try to identify the best parse,
yes.
the best path in the word graph.
Right.
And then you count by the normal error measure
Right.
what the problem is.
Right.
Yeah, okay.
And the CA column is almost similar, but this time we were not comparing the words, but actually the concepts. So it's kind of the similarity of the meaning representation that the system produced and the gold standard that was annotated by humans. So this led us to believe that this approach was actually feasible, so that you could actually also get a practical system based on a more symbolic-oriented approach. Okay, so what we did was we took this system and extended it greatly, because now we wanted to do this for general Dutch, not for one particular small application, but for, we don't know yet what kind of applications, more like in general. So the grammar now contains about 300 rules. The lexicon was sort of expanded by including the CLEX, electronic dictionary, and also parole. Well, this is perhaps not known in this part of the world, but there's another electronic dictionary for Dutch. Both the grammar and the lexicon are organized as inheritance hierarchies. I'll say a little bit more about that. The semantic representation, well, actually I don't think you would be allowed to call it semantic, but the representation that the system produced is a dependency structure, and CGN stands for Corpus Gesproken Nederlands, Corpus Spoken Dutch. This is a different project in the Netherlands where they're annotating spoken Dutch, and part of that they also annotate syntactically, and they provide guidelines for annotation, and we essentially follow those. So if you think that the annotation is ridiculous, then we can sort of point to them and say it's not our decision.
And when you say lexicon, 100,000, every morphological form, every component.
Yeah, it's at the moment it's a full form lexicon. Yeah, and it's a little bit hard to count how many full forms are actually recognized by the system at the moment, but as many. And then in addition, the various non-word heuristics as well. So more in particular, the type of grammar that we use is constructionalist HPSG. It seems that this doesn't quite fit on the screen. No.
What?
So the two words that are abbreviated there are constraints. So the idea.
I have no idea what you're talking about. What are you pointing at the little hand or what?
Well, my screen goes like to this. I hadn't noticed this before. So this is constraints, and this is also constraints.
Oh, okay. I didn't know.
Yeah. So we've chosen a variant of grammar, a unification grammar that's now sometimes called constructionalist HPSG. HPSG is a very much lexicalist approach to grammar. So lexical information is very important. It inherits a lot of ideas from categorical grammar. And constructionalist HPSG is going back a little bit more to what used to be called, I guess, GPSG. So there's also constructions are taken as you can also actually have rules, say. So, and we've chosen for this particular approach to grammar writing because it seemed to combine two advantages. On the one hand, you want to be able, as a linguist, say, to specify very general things. So, and if you have a certain idea about how, for instance, how subcategorization works or how /inheritance works, you want state it only once, and you don't want to sort of go through all the rules and add the same thing over and over again. On the other hand, from a, say, a computational perspective, a parser loves to get as much perhaps redundant information as possible in order to sort of reduce the size of the search space as quickly as possible. So what we try to do is combine these two benefits here. So what you get is there is a lot of distinct grammar rules, but there's a lot of similarity between them, and this similarity between similar rules is expressed because they are instantiations. So each grammar rule is an instance of a kind of a general structure. So there might be a grammar rule, S goes to NP-VP, say, but you don't specify much in this rule. You just say, well, it's S goes to NP-VP. And in addition, this is an instance of a head complement structure. And then the head complement structure knows that there are various things going on which are typical for head complement structures. And in addition, it knows that it's an instance of a headed structure. And the headed structure is yet a level higher up in the hierarchy. Even more general constraints are associated with that structure.
Excuse me. So there is a rule, and the rule has annotations. Is that the point? That this isn't a regular S go to NP-VP rule, but the VP has to bloom into something, and the NP has to bloom.
Yes. So remember,
so
this is.
Excuse me. So this is as if you put a subscript to VP.
No, I don't think so. No. Remember, this is unification grammar. So S goes to NP-VP means there is this big feature structure.
Yes.
Which has category S and a lot of additional stuff in it.
Yes.
And NP as well, and VP as well. So there is this rule S goes to NP-VP, and then there is a lot of feature sharing going on between the daughter categories and the mother category.
Yes.
And those feature sharings are very often typical for more general than for this specific rule. So a lot of the information that is flow that is going on is not expressed in this particular rule, but it's expressed in a scheme. So this rule says I am an instance of a general scheme, and in addition there are various feature equations specific to this particular rule. So perhaps exceptional for this rule.
So, but once you specify them, everything underneath has to conform to that.
Right.
So why isn't it like having a list of what this could be, and this is one of a list?
Is your inheritance hierarchy defeasible?
Sorry?
Is it defeasible inheritance?
Yes.
Okay.
Yes, you can inherit from the structure, but then say, well, but instead of in general this feature equation holds, but in this particular case I'm just going to ignore it and I'll assign it a different feature anyway. You can also do that. So you can have exceptions to those. Yeah. Okay. Now in addition, so I guess I said some of this already, but these structures, these nodes in this hierarchy can be associated with various principles. So that's where the HPSG speech comes in again. So the head feature principle and the fill-up principle. These principles are not expressed as logical implications, as is in standard HPSG, but we just associate them with a node in this rule hierarchy, and that's somewhat more, well, it's computationally more, well, just easier to do.
Sorry, could you explain that again? So how is the filler principle or the
So, for instance,
hierarchy?
the filler principle is in standard HPC, it's expressed as an implication. If a feature structure looks like this, then in addition, this must hold.
Right.
And that's sort of hard to keep track of where this feature structure might occur in the grammar. And here we just, here you can sort of compile it offline, because a rule is an instance of a more general rule, and at some point in the hierarchy, at one node, this principle is associated with that node. So its effect is simply computed at that point. Okay. Now, the lexicon in this type of grammar is also very important, of course, especially we're very sensitive to subcategorization frames. So subcategorization is very important. The selection, verbs select for certain complements. So that's very important, and that's where the system sometimes breaks down if you don't have that information. Just a matter of terminology, I will be talking about tags. So the lexicon is a mapping from words to tags. But what I mean by tags, it's just a nice and small word, but it's really a bit more than a part of speech tag. It includes both, say, the morphological information, like noun and singular or plural, but it also represents whatever information is that you have for that word in the lexicon. Okay. Okay. So I'm going to say a little bit about lexical analysis, because that's where this part of speech tagger later will be related to. So what lexical analysis, of course, is, well, you get a sentence, you look up a word in the lexicon. In addition, sometimes you don't find the word in the lexicon, so there's a number of heuristics to assign it a tag after all. And then we do two things. In this type of grammar, words are typically associated with very many tags. And a lot of those are, you can immediately see that in this particular sentence they are ridiculous.
You know what?
In a particular sentence, you can often immediately see that a certain tag is ridiculous. For instance, for the verb count, one of its entries will say, well, I require a particle up and some other things to count someone up, right? If the word up does not occur in the sentence, then that entry is completely useless right from the start. And it turns out that there's a lot of such co-occurrence restrictions between these tags, and we simply filter out all of them. And in addition, what we try to do, so this is meant to filter out impossible tags, but what we also do, and that's what I will come back to later, is to filter out unlikely tags. So
Filter out what tags? Unlikely.
Unlikely. So if you just think, well, it's probably not going to be useful to have this entry here, then try to filter those. And how we do that is we do that. Show that
You mean
later.
syntactically unlikely or semantically unlikely, or in this context?
Yes, in this context. So we're going to use a standard part of speech tagging technology for that. So based on the surroundings, essentially.
Okay, so syntactically unlikely.
Sorry?
Right, so just syntactically unlikely, not semantically unlikely.
Right.
In fact, the precise statement is HMM unlikely. The HMM
Yes.
thinks it's unlikely.
But in the HMM there are
Whether
no
it's syntax or semantics.
relations between the words, only between the tags. So I guess there's not really semantics there.
Well, but the tags are not just part of speech tags, right?
They include more
HPSG
information.
They're the HPSG lexical entries.
Sorry?
They're the HPSG lexical entries, right?
Well, they're names for that, really. Names for these feature structures, yes.
If you needed to say how big the tag set was, could you give a number for it?
It has 4 zeros. It's like 20,000, something like that.
So this is a little bit like, the true journey grammar super
Yes,
tag.
it's a little bit like super tag, yes. So just to give an example.
This is just a computational trick. It doesn't make matter. I mean, if you didn't filter them out, you would just have to work harder,
Right.
but it
Right.
would still not be there. I mean, it's not essential to the grammar, it's only to speed things up.
Right. That's right. Right. Just as an example, for this particular sentence, Mercedes would have announced its new model yesterday. The lexicon assigns 132 tags, and only 22 of those are possible. So in this particular case, the co-occurrence restrictions filter out really many tags. And then we also apply this tagger, and then we only keep 18 tags. Now these 18 tags are then mapped to the feature structures, the HPSD signs, and we get 72 because that's a one-to-many
I don't
relation.
understand. The normal HRM tagger that I know of would assign a single tag for each.
Right, I'll come to that.
That's not what you mean.
I come to that.
Right.
So that I will show in detail how it works.
Okay.
Just so we end up with 72 signs as opposed to more than 1,000, and I guess you can see that helps.
And excuse me, so for instance, the Apple word is that Mercedes could be Mercedes Jelinek, meaning the woman after which Mercedes is named, and then it could also be Mercedes the company.
No, I think the first reading is Mercedes as a proper name, and the other one as the how do you call that?
It's a company.
No, as it's like a determiner. No, like an adjective, I think. Like an adjective.
Automobile.
It's an adjective, as if it could be the adjective of Mercedes. So the heuristic in this case, perhaps silly, but that's what it also does. Okay, so we'll come back to how this tagger works a little later. Just to go forward with the overview, I'm not going to say much about the parser. I've done that enough in the past. But ask me if you want to know more about it. It's a left corner parser, and there's memorization going on and goal weakening. Goal weakening is, I'm not going to say much about the parser. Ask me if you want to know. The grammar does allow certain delayed constraints, so more powerful than the normal feature equations, and we make sure that the parser is able to treat those as well, and especially with memorization that gives certain problems and try to solve those. And the parser, of course, most of you will know, especially in this type of grammar, you will assign a lot of different parsers to one given sentence, and for that reason your parser better not enumerate all of them. So what we construct is a so-called parse forest, and it's a compact representation which somehow contains all the parsers. Okay, and just for those people who have never seen this, this is a graph showing from left to right the sentence length, and this is actually what our system assigns to the sentences on the corpus that we use. So left to right is the sentence length, and from bottom to top is the average number of readings for that sentence length. And I'm not sure whether you can read it, but this goes from 0 to 5,000 up to 15,000. So up to sentences of length 10 or 13 or 15, things are okay, but then you can really see the exponential behavior.
Is this the number of possible density of the parse forest, or something?
This is the actual number of parsers, if you would all generate them all. And I stopped with 19, I think, because there was one sentence with 19 words that had more than 500,000 parsers, and then I thought this is clear enough. So that's why we don't generate them usually, only to produce this graph, right? So what we do, we have this parse forest, and we want to extract a parse from it, and in particular we want the good one if it's available, or otherwise at least perhaps the one that is as close as possible. So let's say the best one. So we need some kind of a way to score a parse tree, so to determine how good it is. But that of course is not good enough, because then you would still have to enumerate all of them and then assign them a score and then pick out the best one. So of course that's not possible. So instead we make sure that this function that scores parse trees is able to score partial parse trees as well. And then we, while extracting a parse from the parse forest, this search is organized as a best first search. So and the best first search with a beam. So we can't really be sure that we will find the best parse. That is because, as we'll show later, this function sometimes uses kind of global information as well. So I don't think you can really efficiently produce the best parse. But using this beam, we can, as this graph shows, we can typically find a very good parse very quickly. Now this graph is a little old, so the actual numbers in the meantime have gone up quite a bit, but the differences are still similar. What does it say? So on the left column there's the beam that we use while searching for the best parse. So if we only work on the very best one and throw away the rest, then the accuracy is dropped to 73.63%. I'll tell you later what this accuracy actually is. And of course in that case it can be quick because there's little possibilities to choose from. And if you go up, so if you make the beam wider, then the accuracy goes up, as you can see. If you go down, the accuracy goes up and the speed goes up too. And for this particular experiment we couldn't go beyond 32, then for some senses the system ran out of memory. So
that's why it gets worse, because already it's suffering from. I mean, it gets worse.
I think that must. I don't understand why it gets worse. So I just think it's random noise, or there is something going on that I'm not aware of. Okay. Now, finally, I'll say a little bit about the structures Sorry.
It's not surprising that, not surprising. The fact that the accuracy actually goes down means that what is most likely according to the model is not necessarily the most accurate. So this is telling you that your model is mismatched to the ground truth. I guess the right thing to do would be to compare the likelihood of the correct parse under the model and see if it turns out to be lower than whatever parse it found. And if it did, then you know that accuracy going down is not a failure of the pruning, but in fact a failure of the models to model the truth. Well,
maybe, but I think these differences are not significant anyway. So this is a fairly small experiment. So. But I'll have to redo it anyway because the numbers are too low generally. So we're now in about 80% all the time. So these dependency structures, you might perhaps wonder why not take an annotation format.
Why not what?
Why not take a similar representation as the Penn tree bank, say for instance, like a syntactic tree? Why isn't that good enough? So these dependency structures have been argued for languages other than English, like German. There's a Negra corpus for German where they do something similar. I think there's a Czech project where they do something like this. So they're supposedly suitable for languages that have freer word order than English. Now Dutch hasn't that much free word order, but a little more than English. And also we're going to use the dependency relations that are in these structures in our disambiguation component as well. So these dependencies are useful in themselves. So that's another reason why we're interested in this format. And as I already told you, this is the format that's actually proposed by other people, so it seemed like a good idea. So this is an example, just to, it's a bit strange. Normally in a dependency structure, you will find the word in a node. So what do we have here? De sentence Chevrolet brengt voor 1970 een nieuw model uit. Chevrolet verb for 1970 a new model particle. So you can see that in this particular case, the head is shown here as a branch of the node, and normally you would expect that the head itself is the node. It's just a little quirk that
I
is.
don't understand your point.
No.
I'm having trouble reading the
Why don't you point to it?
All right. Okay. I'm on my way. So normally in a dependency structure, the head is sort of given here,
Right.
and here this turns out to be the way that these people illustrate these dependency structures.
But the verb is the head of what? I mean, of course it's the head of the whole sentence,
Yes.
but I mean, how am I to read the graph? That it's the head of the noun and
So
modifier or what?
So it's the head of this node.
Yeah.
There is a modifier of this node, that's this thing here, the prepositional phrase. There is a direct object, obj1, of that node, which is the noun phrase. And there is an SVP separable verb prefix, the out.
So to get the standard dependency structure, I would take every node, and amongst all its children, I'm guaranteed that only one of them has this HD annotation on it, and I would put that on top.
Yes, yes. So there are a few other differences that I haven't talked about, but yes, yes. In addition, we have co-indexing going on. So for instance, in control, John tries to kiss Mary, then the subject of tries would be co-indexed with the subject of Mary. Kiss, what did I say? Kiss was the verb. And so you, in some cases you would end up with a graph rather than a tree. Okay.
I mean, this is not how it would be drawn in a dependency way, right? This is in fact drawn as if it was a phrase structure. Parse.
I don't think that it's really important at this point, but
Well, I thought you made a point that it is.
yeah.
that
Well,
it
I
is-
just wanted to warn you that the way the things are illustrated here look a little different than you might expect. I was just hoping I wouldn't confuse you, but perhaps I do.
So you're saying that, like, the illustration may not look like a dependency structure, but all the information in this is really
Right.
just a dependency.
Right, I think, yeah.
Yeah,
I
but-
should have said that, I guess.
But the whole point about dependency, I understood from Czech, is that in Czech branches cross. And
Okay,
in English
okay.
they don't cross.
So this
and
is
and therefore they don't want to use the structure grammar because things will be crossing.
okay. So and that, if you look at it from that perspective, then this is a too simple example.
Exactly, it's too
Right,
simple, right?
Right, because
Because nothing crosses.
no, but it easily could. Well, in fact, there's no reason that these leaves are in the same order than the string is. That's not a way to say the same thing, right?
Okay.
Yeah. I better hurry up a little bit here. So one of the things that we're doing is building a tree bank. Well, it's not a tree, but a bank of dependency structures. And I think I'm going to skip this, otherwise I won't have time to talk about the other parts. I will have to say a little bit about this. In these dependency structures, the relations, the dependency relations are somewhat implicit, but we can make them explicit. So in this example, we have Kathy sees them wave violently, and from that dependency structure we can extract the dependencies. So we take the head of a node and we take another. So in this case the first one is Z, that's the head of the top node, and then we take one of its relations, for instance subject, and we take the head word of that. In this case that would be Katie. And so we can map the dependency structure to all the dependencies that are there, and we use that to compare dependency structures. So for instance, if the system produces a dependency structure and we have a gold standard dependency structure, we want to determine how good the system performed. So we want to see how close these structures are. So what we can do is just simply take the dependencies in the first one, and so it's a set of dependencies, and we can take the set of dependencies in the gold standard, and we could, for instance, compute precision and recall and F measure.
Are these labeled or unlabeled dependencies?
What do you mean labeled?
On the
They're like these triples.
In other words,
So the obj1 is
Yeah, so you're counting on one. Okay.
Right.
Labeled.
so the fact that head is dependent on Z, if it didn't have the tag obj, then you would say it's wrong, even though you would have the dependency correctly.
Right. No,
but if the label is wrong, you say it's wrong.
Right. That's true. And we're not working with the F-score. We do something that's slightly different. So we use something that we call the concept accuracy. So we take the number of dependencies found in the system, DS, and DG is the number of dependencies according to the tree bank, and then we can say, well, there is a number of wrong or missing dependencies. So they're wrong if they didn't occur in the gold standard, and they're missing if they're missing, right? So concept accuracy, we divide the number of arrows by the maximum of the number of dependencies in either the gold standard or the system analysis. And this is a slightly, well, you get slightly...
It's a little optimistic, right?
Sorry?
It's a little optimistic.
Optimistic?
Yeah, because you divide by a bigger number, and so the negative thing is less negative.
No, I think it's fine because DG is a fixed thing, right? You have no control over it.
Right.
And so in fact, you do best by making DS equal DG.
Yeah.
Because any less, and you know that whatever you didn't hypothesize counts in the numerator anyway. Whatever more, it's not going to count in the denominator, and if anything, it's going to be net.
So what I think what it's as
to
if
the extent that that other thing is bigger, it's got to reflect itself in the numerator as well.
You can't
Yes,
hypothesize both things that's
Right.
smaller.
Right.
So
well, typically what you get is like the minimum of precision and recall. So it seemed in our experience that if you were not hypothesizing anything, then you got a too high score. You got sort of rewarded for not saying anything, and it seemed silly. So this gives you kind of the minimum on a per sentence level. But of course, the scores are lower than you might have seen somewhere else, and that's of course what I worry about a little bit. But I think it's a better indicator for the quality of the system. Okay, so now I'll quickly go on with how we do disambiguation. So I guess I already mentioned that we use a log linear or maximum entropy model. So the motivation for that is that in such a model you can combine various types of information, and you don't have to worry about whether these different types of information are independent or not. And normally this would require annotated training material, and that's what we're going to do. So the probability of a parse Y given a sentence X is given here. Let's start from the inside out. So I guess many of you might have already seen something like this. So I are the various features or properties of a given parse. So what we do is we count how often in a particular parse a particular feature occurs. That particular feature has a corresponding weight. There's a lot there here. So the frequency is multiplied with its weight. And we do that for all features, and then we sum. So that's this part. That's the easy part. Now, if you really want to get the probability, then you have to take the exponent of that and then divide by whatever you get if you do this for all parses. Okay? But really we're only interested in the best parse, so we just ignore all of that. So we just really only do this. So we just, for a given parse, we compute this. The weights can be positive or negative. If they're negative, then that means the system thinks this is a particularly bad feature. And you can then just take that parse that has the highest score. So That's really straightforward. We need to worry about two things: the features and the weights. So the features, what we did is the following. So a rule name, remember there were about 300 rules. A rule name is a feature. There are various unknown word heuristics. Each of them is a feature. We have features to distinguish between complementation and modification, long distance dependencies versus short distance dependencies, minimal attachment versus non-minimal attachment. And here you could really use your linguistic imagination if you're happy to have something like that, and add whatever you think might be useful. So people have tried to come up with features that determine for a coordination whether the coordination is balanced, whether the conjuncts are similar or not.
I don't understand how a rule name would be a feature. In other words, if you have a lot of nouns that may be good. Feature is something that you count up, right?
Right.
How many, so
in a
feature
particular
should be
parse,
either,
in a particular parse, you can look which rules were used in that parse.
right.
So, and each rule has a name, I mean that's.
Yeah, that's right.
So if you use a rule like NP goes to that N,
Yes.
and then you sort of, and you see that rule 3 times, and then you've seen that feature 3 times.
Yeah.
And in a competing parse, you perhaps produce the NP using a different rule, and so you get different counts for your features.
What I'm not seeing on this slide, and maybe it's on the next slide, is lexicalized features.
Yeah, that's why this is 1. So the next one is that every dependency triple is a feature as well. So, but in addition, we use for those we use backtail features. So there are 3 fields, and for each field you can also sort of have a ignore value, say a don't know value. And then suddenly, in the previous sheet there were 400 features, and now we have 155,000 features. And we've tried various ways to reduce the number of features. And
so when you have A, B, C, where C modifies A and B is the relationship of the modification, what do you back off to? Do you back off
to a very generic part of speech. So things like verb, noun, preposition, adjective, adverb. I think one of those 5.
So the backing off is in the label of the dependency.
Yes, not in the relation. Only in the words are replaced by the part of speech.
Okay, so the backing off is in the lexical part.
Right.
And the label stays the same.
That's right. Now you also need to get at the weights, and most of you probably know more about that than I do. So I'll just refer to. I just mentioned work done by Robert Malouf, colleague of ours, who has done this. He's moving to the States this summer. So if you're interested in this, you could easily invite him next year, perhaps. So I guess since we didn't know any better, we started out using improved iterative scaling, since that's what people had sort of suggested that you should use. And later on, it turned out that there were better ways to do it. And so the conjugate gradient method and the variable metric method works much better. Can you see the green line? Okay. So this shows
The green line that goes down completely.
right. So the green line is the new method, the gradient. No, it's the LMVM method. So this shows the number of iterations from left to right, and the KL divergence. So that's how close you are to what you want to get at. So it's this supposed to convince you that works much better.
What you're seeing here, it looks like is superlinear. Is the superlinear convergence?
Sorry?
It looks like what you're seeing here is the superlinear convergence.
I don't know.
So as the thing flattens out, you're not creeping.
No. So this is exactly what with IIS. I never knew how much iterations I would use today, right? So if I was very optimistic, I said, well, let's do 300 iterations. But if I really wanted a very good system, I would want to let it run for a long time. And this is just immediately converges and will just stop after a minute or so. It's really quick. implementation is available from Mr. Malouf. So, one thing I haven't told you is how I get the training material. So, the features I've discussed all require a full parse. So, they require, for instance, the rules that were applied. Now, in the tree bank, the dependency structures, these rules are not even represented. So, how do we do that? So, what we do is we use the parser to construct the training data. So, we do this as follows. We create, say, the first 1,000 parsers for a given sentence. And for each of these parsers, we compute its accuracy. And then we treat that accuracy as if it were a frequency. So we add each parse to the training set with a frequency that is proportional to its accuracy. Okay? So because in these full parsers you get all the features. Now this seems to work very well, and I believe that this way you also give some weight to very bad parsers. And it seems to me that this means that you don't, or that this is the reason that we don't seem to get much overtraining here. Although I haven't shown you that we don't, but believe me, there's not much overtraining going on. Okay, let me just.
So let me see if I understand. Actually, the formula that you have, the maximum entropy formula, is really a probability formula. And you need to, of course, find out what the lambdas are. And you've decided that there are certain features which might be helpful in deciding whether this parse is good or bad.
Right.
And so for each feature gets a count and a lambda, etc. And then you've got to evaluate the lambdas. Now, normally you look at it from marginal constraints to see if the feature, quote, fires or not. And then there is a target, and you make the target. You essentially try to adjust the lambdas so they meet their targets. And the targets are what you now said. In other words, you did some parsing, the best parsing you could. Of course, with an inaccurate parser.
Yeah, a parser without disambiguation at all, right?
Well, you still have to decide what parse for each sentence.
No, it just uses the first 1,000, all of them.
Oh, it uses the first 1,000 and takes and when it says accuracy, it's an average of those accuracies.
No, for each parse, you add to the training set with a frequency that is proportional to its accuracy.
So for each sentence, you might have 1,000 parses.
Yes.
And each result, each parse has a certain accuracy, and you put it there.
Right.
And of course, each parse has certain features firing or not.
Right.
Blah blah blah.
Right.
And now you do it for, I don't know, for your whole training corpus.
Right.
And this is what's going to get you the targets from which you will evaluate the lambdas.
Yes, that's exactly right.
And then later on, once you're done with it, you're going to use that measure to select the best parse from the 1,000 or whatever number of parses, or from the parse forest that you have.
Yes.
And that will be the measure that will select the best parse.
Yeah.
And this is sort of bootstrapping, and presumably you now get something better.
Yeah, although we're not using the disambiguation model in the production of the training material.
No, I understand, but
there's another question.
So it's a fractional count, right? So each, like if you have 1,000 best parses, each like one best parse contributes to each n best contributes some fraction depending on the slightly.
Depending on.
So when you train when you get the maximum entropy features, you weigh the features by sort of likely.
Yeah, you mean that we sort of normalize if a sentence has less parses?
Right. No, suppose it's a best parse, you weights count differently from the 100 best parse, right? So there are two parses and best.
So if they're better, conceptually we just add it a few times in the training material, and if it's worse, we just add it a few times.
And you could presumably iterate, right? In other words, you could take your maximum entropy measure, then select the best parse, and again get the targets out of that.
No, but we're not actually using the best parts for the training. We just use all of them.
I understood you,
Okay.
but I'm saying that you could have another
We-
round that
could
once
do
you once you get the lambdas fixed, you can now select from the 1,000 parses which is the best,
Yes,
and now you could put that back into the training
only
to
that one.
estimate the lambdas.
Only the best ones.
Yes.
We haven't tried that.
They do have an interesting problem though, that their features may not, there might be features which are not even represented in the gold standard of the parse, because the gold standard is only a dependency structure. And as a result, you wouldn't even know how to compute its expectation. So
Well, you would also need the parse.
what they're doing is a little bit more clever. They have a very complicated parse model, and for each parse that they generate, they just count what its accuracy is, and that weighs the number of times you saw a certain feature in your training.
I thought I understood it, but maybe not. Okay.
Well,
Okay. Yeah,
Both
well,
of us.
anyway.
We can talk more after
this
this.
is
We're getting close.
I just want to make sure that I get the results as well here, right? So I like to think.
So you raised it from something like 76 to 90, is that
To
right?
80.
Oh, that's possible.
Okay, there are two. There's a baseline.
To 80, right?
The first line is the best possible is if you somehow knew which of the 1,000 parses
From
you
the
should.
1,000 that you
Yes.
have.
From the 1,000.
So it's an oracle best.
That's the oracle best.
Yeah.
So that gives you kind of a measure how good the grammar is, you could say. Right? And the baseline is if you would, well, I think I should have measured what a random parse would give you, but this is actually what the first parse gives you. But that it's arbitrary. And the system is complicated enough that you can't really tell which one is the first parse anyway. So the baseline is about 60. So this is a kind of number that you can remember. So the space is between 60 and 90, and we get about 80. So we're solving 2/3 of the problem. Okay, there's 1/3 to go. Okay, who's in charge of the time?
We started
Yeah.
we started at 5:34.
We also started late because Fred
Started
was
late,
getting his
so
letter,
Another maybe.
but so I didn't say that this. I didn't say anything about this part of speech tag, and I was hoping I could sort of quickly go through that.
Please go ahead.
Yeah.
Okay.
This
Okay.
is in the abstract and it was interesting.
So to make a little bridge from that to this, so this was all supervised learning, and I think in order to get this remaining third part of the problem, it seems that it might help a little bit to create bigger tree banks, but really you would need enormous big tree banks. I mean, it's unrealistic even for English, let alone for non-English. So you should also really try to do things in an unsupervised way. So here we're going to see a semi-supervised, unsupervised technique, and only it's applied for different tasks. So that's the bridge. So what we're going to do is try to speed up the parser. I've already said that earlier. Try to speed up the parser by reducing the number of tags for any given word by training an HMM tagger. And the interesting part here is that we are not going to say sit down, annotate a corpus and train on that corpus, but we let the system annotate the corpus. So actually we're not going to learn what people think is the best tag sequence, but we're going to learn what the system will turn out to be using anyway. Okay? So we just take the system without this tagger, and we apply it. I think we should have that here. Okay, I'm going to.
What are we doing?
I'm trying to compress this a little bit. Okay, we're just going to use a very standard HMM tagger. The first one you can think of. It's probably the first one in any book on this topic. So it's bigrams. It uses. We're not even going to train it in any complicated way. We just use direct. I'd better slow down, otherwise it takes more time. So we're going to estimate the probabilities directly from the corpus. So what we have is the probability of a tag given the previous tag, and the probability of a word given the current tag. Okay. Now, normally what people do is you select the best sequence, but here we're going to we've tried that, but that doesn't work so well, and apart from that, it seems a bit too hard to expect the tagger to find precisely the right sequence of text. So we would be happy already if it just throws away half of all possible text and let the rest of the words still be a little bit ambiguous, but not as worse as it was. And we do that by computing both the forward and the backward probability. So we compute the forward probability, compute the backward probability, and then for n given tag, we look at its competitors on that position, and we throw away the competitors if they're much worse. Okay, and much is a threshold. And since we produce the training material systematically by a system, we can actually produce a lot of it. So for this experiment, we used 6 months of newspaper text. That's and only for the sort of the easy sentences, otherwise it would take too long. But that still is almost 5 million words. And if I retrain the system every now and then I use the full year, so it's almost 10 million words. And we've tried, and this works very well. Okay, I'll just immediately go to the result. So we evaluated this. So the top line is what happens if you don't do anything. So there's no.
You don't do anything?
You don't filter anything. So you let the system use all tags. There is no part-of-speech filter.
The system is an HMM tag, binary
okay.
tagger. What is the system?
It's a super tagger.
Right. So this is the system as a whole without a tagger in it. Okay, just as a baseline.
System means
the parser, the whole parser. Yes.
The way we discussed it before.
Right.
Yes.
Okay. So in that case, we don't do any filtering apart from the rule-based filtering. Then each word has about 3.5 tags on average. Okay, and parsing takes on average more than a minute. Okay, and accuracy is almost 75%. Again, this is an old experiment. Numbers are somewhat higher now. And depending on the threshold, which is the first column here, we can either filter very aggressively or we can be more liberal. And if you filter aggressively, then the remaining ambiguity of a given of words is low.
What is the one on the top?
Well, that's I think the number.
1, 2, 3, 4, 5.
That's the value of the threshold, and I have to remember what it actually is. I think it's the number of orders of magnitude that it has to be worse.
I see. Okay.
On a binary scale, I think. So in.
And that's why we still have 1.58 tags per
Right.
word.
And so that's very aggressively. You throw away a lot, and the parser is almost is much faster. And accuracy, and this is sort of a surprise. Accuracy was not going down; it was going up. So it actually helps to do this. So there are 2 explanations for that. One is that this information itself is perhaps useful for disambiguation, and we didn't include those features in the disambiguation component. And there is another artifact that I didn't really talk about. The system also has a kind of a robustness mode. So if it cannot find the full parse, then it will try to find partial parsers, not non-overlapping partial parsers. Now it turns out if you allow too many tags, then there almost always is a full parse, but not a very good one. Whereas if you throw away the bad tags, then the system sort of doesn't hallucinate and will produce partial parsers. Now, of course, that's perhaps not as good as a whole parse that is correct, but partial parsers that are more or less correct is better than a full parse that's completely wrong, right? So that's why this really works. So this gives some promise that you can get somewhere in this kind of bootstrap approach. And the sheets I'll skip because I'm over my time. But what I would like to do is sort of get something similar done for the disintegration part, some kind of semi-supervised bootstrap method. And the initial experiments.
I don't get how is this supervised at all? Because of the initial statistics which were obtained by hand, is that why you call it semi-supervised?
Yes, because when I used it unsupervised, people start complaining.
No, but you call it semi-supervised because the original statistics like of the P of P prime into P, etc. are obtained from hand annotation.
No, they are obtained from corpus that's produced by the system.
Oh, they are obtained from the corpus system.
So
this is
it's
solipsistic.
Right.
Whatever the word may be.
So if you look at the actual technique, it's a supervised technique because you have a training corpus annotated.
Right.
Except in this case, the annotation is not done by hand, but it's done by the system itself. In the previous phase, that's if you step back, then it's more like unsupervised.
Yes.
So
Are there any questions from people who haven't asked something yet? Yeah, John.
My question is designed to elicit a subjective response, and it is: do you guys feel that the ambiguity that is exploding when you parse these sentences of Dutch with this grammar, is it mostly, does it seem to you, due to lexical ambiguity because the grammar is so highly lexicalist, or is it due to constructional ambiguity about which construction sentence exhibits?
Or does the grammar just overgenerate?
there's a little bit of that too, but not much. Well, it depends a little bit how you define it, of course, but most of the analysis that you get, which you get too many of, can be sort of have motivation if you just change the words perhaps, or think of a. So it's not completely silly, but of course, and to answer your question, you really get both. Mm-hmm. For the lexical ambiguity, we now have a kind of a cheap method to reduce it immediately, say before the parser actually starts. So that's really useful. I wouldn't know how you could do something similar for structural ambiguities, but you get those a lot as well. And actually, this is a bit of a frustrating part to improve the system, or try to improve it. You sit down, well, this particular linguistic construction we haven't no handle for yet, so you start adding a rule or do things slightly more differently, and then at the end, you still get this 80%, and the top line has gone to 91, and the baseline is dropped to 59, and it, have you made any progress here? That's sort of worrying.
I just have another subjective-ish question, and that is, when you find lambdas that do work well, do they tend to be kind of equal to each other? Like, is the lambda associated with the head specifier rule about the same as the lambda associated with the head complement rule? Or do the lambdas seem to be stratified into
I have no intuition whatsoever. I've given up trying to understand what these weights mean. No, it's very, no.
Are there maybe like
I'm typically happy if a feature actually gets a positive value if I think that it should get a positive value, and vice versa, and a negative value when I think it's bad. Other than that, since these features are not independent, it might well be that a feature you think is very important doesn't get the very high weight because of other features that somehow interfere, and it's good. I don't understand that.
Okay, thanks.
Anyone else? Okay, well, let's thank the speaker.